Hi, Assalamualaikum and a very good morning. So today we're going to do some past equation for the year of 2020 and 2021. And we're going to discuss the past equation for the chemistry program in the matriculation, which is the code of SK025. So before we go straight into the question, let us look into what is given during the exam. And as far as you know that, for the chemistry program, there will be no formula will be given. So formula is not given in the exam. But what is given to you is that you're going to be given a table of the relative atomic masses. So they're going to be a list of elements with their symbol, and you're going to be provided with the atomic number as well as the relative atomic mass. So the relative atomic mass here is referring to the molar mass. Also, you're going to be given the list of constant. So here are the list of constant that's going to be given. For example, the ionization constant for water, speed of light in a vacuum, and any other stuff. But for this semester 2 program, we're going to focus much on this particular constant. So I have already highlighted it here. For example, the specific heat of water. So it's going to carry a unit of C, small letter C with W. So it's going to carry a unit of 4.18 joule per gram and per degree Celsius. So you're going to use it often in chapter 2, which is related to thermochemistry, particularly used in order to answer the calorimeter problem. Next, you're also going to use the list of the molar of gases constant R, which is the universal gas constant. So the universal gas constant will have two values, but for chapter 1, we're going to use the value of 8.314 joule per Kelvin per mole in order to answer the chapter 1, which is reaction kinetics. And this R value here will be used in order to answer the Arrhenius equation. And the next popular list of constant is the Faraday's constant, which is 1 Faraday is equal to 96,500 Coulomb. So you're going to deal with that in chapter 3, focusing on the idea of the electrolysis in the electrolytic cell. So here are the important stuff that you should know by the beginning of the exam. So without any further ado, let us go straight into the question. So for question number 1, the decomposition of the gaseous hydrogen iodide Hi at 508 degrees Celsius is represented by the following equation. So two Hi gases will be decomposed into the hydrogen gas as well as the iodine gas. So the molar concentration of Hi was measured at the time interval in second. So they are given the unit of second. And the graph of the concentration, so concentration for the concentration against time for the decomposition of Hi at 500 degrees Celsius is shown in figure 1. So here are the graph of concentration against time. So based on the figure 1, we need to determine the order of the reaction, and we also need to write the rate equation for the decomposition. So for this question, we need to determine the order. Okay, so is it a zero order, first order, and second order? So how can we do this with the information given? So usually in the question, they always stated that this reaction is a first order reaction. But for this problem, they doesn't provide you with any hint. Okay, so they doesn't give you the unit of rate constant. Okay, so usually when you're answering a question, when they give you the unit of rate constant, let's say per second, you know that it is a first order, but then they didn't give you anything. So for this reason, we're going to look into another hint, which is by looking at the half-life. Okay, so half-life, we can look at that and we can figure it out from the graph that has been given. So unit of rate constant is not given, so we can ignore that. We're going to focus on the half-life. So from the half-life, initially, our initial concentration is 0.10. So if we were to divide that into half, we're going to get 0.05. And then if the 0.05, we're going to extend that to the time, which is below here. We're going to get the time here to be 125 seconds. Okay, And then we're going to divide that again into half. Okay, so this one is our first half-life. So our first half-life from 0.1 divide by 2 because half-life 0.05. And then we're going to divide that into 2 again. We're going to get 0.025. So similarly, we need to figure out the half-life for the second half. Okay, so we can say that at the second half-life, we're going to get the concentration at 0.025. And then we know that the initial concentration, the time here is 375. And then we're going to deduct that with the blue line here, which is 125. So here is 125. So the distance from there to there is 250 because 375 minus 125. Okay, so the total distance that we're going to get for the second half-life is 250 seconds. And from this comparison, you can say that the second half-life is double than the first half-life, 250 with 125. So since the half-life is double, then we can say that it is a second order reaction. If the half-life is the same, let's say T1 at the first half-life, T half is the same as the second half-life, then it is a first order. But then if it is doubled, then it is a second order reaction. So from here, from your drawing of the graph, which is the sketching here, as well as this statement, you can say that it is a second order reaction. So we have answered the first question. And then we need to write the rate equation. So when we need to write the rate equation, we should start our sentence with rate equal to K, which is our rate constant, and then the concentration of the reactant. So our reactant here is Hi. So Hi, and then our order of the reaction is 2. So second order. Okay, so it not necessarily equal to the stoichiometry. It need to be depending on the order of the reaction that we have determined. Okay, yang ini kebetulan lah 2 dengan 2. Tapi sebenarnya tidak semestinya. Alright, so the rate equation, you can say that rate is equal to K, the concentration of the reactant, which is Hi, to the power of 2. Okay, so since we know the rate equation, now we can use that in order to calculate our rate constant K. So from here, we can determine our rate constant K by using the half-life for our second order. So half-life for second order formula is T half is equal to 1 over Ka naught. So our T half here, so our T half in the initial is 0. Our first half-life is 1 to 5 seconds. So we're going to put as 125, which is the blue color here. And then we're going to put our formula in, which is 1 is still 1. Our K is we need to figure out. And our initial concentration is 0.10. So we're going to plug in here. So we're going to solve the mathematics here. So here is in second. This one is in molar. So once you do the math, you're going to get K is equal to 0.08 per molar per second. Okay, so you're going to be K going to be up here, and then second going to go down. So it's going to be per molar and per second. And now we're going to determine the initial rate for the decomposition. So in order to do that, we're going to put rate is equal to K Hi to the power of 2, similar to the one that we have written. But now they are talking about initial. So we can say that initial rate is equal to the K, which is the rate constant, Hi at the beginning, at the initial stage. So our initial rate is equal to K, which is 0.08 per molar per second, multiplied by our initial concentration of Hi, which is 0.10 to the power of 2. And we're going to get our value to be 8 times 10 to the power of negative 4 molar to the power of 1 per second. So we can determine the unit as what you can see here, 0.08 per molar per second. And here is the unit is molar, but then it is to the power of 2. So overall, it's going to be m to the power of 1, and then per second going to be here. So the unit here is insisted. So mesti and diwajibkan menulis unit. Tanpa unit adalah salah. Okay, so be careful of that. Now we're going to look into the next part, which is question 1b. So for question 1b, we need to state the two requirements for the effective molecular coalition in producing a chemical change. So there are two requirements that is needed for the molecule in order to initiate chemical reaction. So first thing first, the colliding molecule, so one molecule with another molecule, when they collide, they must have enough energy in order to overcome the kinetic barrier, or we can say that the kinetic energy need to be equal or greater than the activation energy. Next, the molecule must collide in a correct orientation. Okay, so there are two requirements that the molecule needs to be fulfilled. And as what you have remembered, you're going to be looking at this graph here because the reactant must have enough energy when they collide in order to overcome the kinetic barrier in order to form the product. And similarly, the molecule must collide in the correct orientation. So the green color must collide with the green color in order to produce a product. If they collide in the wrong orientation, no product gonna be formed. Okay. Now we're gonna look into the question number 2. So for question 2a, table 1 shows the list of the standard enthalpy change associated with the solubility of the silver chloride, which is the AgCl. So here are the list of enthalpies with their values. So for 2a, we need to construct the thermochemical cycle to show the relationship between the lattice energy, hydration energy, and the enthalpy of solution of AgCl. And we need to calculate the enthalpy of solution of the AgCl here. So as what you can see here, the lattice energy is given in the positive value. So when it is given in a positive value, you know that it is referred to the lattice energy of dissociation. Okay, so tenaga diperlukan untuk memecahkan ionic solid in order to form gaseous ion. Okay, so that is why the energy is being absorbed. So you know that it is a dissociation. Okay, in order to construct the thermochemical cycle, I will start with the enthalpy of the solution of the AgCl as my target equation. So I have my AgCl solid. So when it is dissolved in water, which is the enthalpy of solution, the ionic solid AgCl will be decomposed into Ag plus aqueous ion plus Cl minus aqueous ion. And the delta H solution here is unknown, and then we need to figure out in step number 2. Okay, but what I know is that the AgCl will be dissociated via the lattice energy of dissociation. So AgCl can be dissociated, which is Le dissociation, which have the value of 915 kilojoule per mole. So it's going to be dissociated into form Ag plus gaseous ion plus Cl minus gaseous ion. Okay, so I have done with this equation. Next, I have the hydration energy. So hydration energy means that Ag plus gaseous ion becoming aqueous ion. So you're gonna make an arrow from the gaseous ion into the aqueous ion. Okay, so the delta H here gonna be negative 465. Meanwhile, for this part, the Cl minus gases, it can be hydrated by having a delta H here with a value of negative 364. Okay, so as what you can see here, you have create a thermochemical cycle between these 4 equations. So we have shown the relationship. Okay, so again, I'm going to show that in a digital form. So you're going to have AgCl solid. So it's going to be dissociated into form Ag plus aqueous ion as well as Cl minus aqueous ion, which is enthalpy of solution. And then you can also break apart the AgCl solid by using the lattice energy of dissociation with a value of 915 kilojoule per mole. And then it's going to form Ag plus gaseous ion as well as the Cl minus gaseous ion. Okay, so I'm going to remove that one. And then this aqueous plus gaseous ion can be hydrated to form aqueous plus aqueous ion. So we're going to make an arrow and we're going to write the value of negative 465. Similarly for Cl minus gaseous ion, we're going to form Cl minus aqueous ion with a formula of delta H. Cl minus equal to negative 364 kilojoule per mole. Okay, so we have made a thermochemical cycle to show the relationship. Now we need to determine the delta H of the solution. So we have the position A going to C. So by mathematics, A going to C is equal to A going to B going to C. Okay, so the initial going to final according to the Hess's law. So A going to C is delta H solution. Okay, so delta H solution is A going to C. And A going to B is the dissociation lattice energy of the AgCl. And then B going to C, we have two equations. Delta H hydration of Ag plus and delta H hydration of the Cl minus. Okay, so we need to figure out this value here. So we can plug in the value of the items that we know. So the dissociation lattice of AgCl is 915, hydration Ag plus is negative 465, and then for the hydration of Cl minus it's going to be negative 364. So once we do the maths, we're going to get the enthalpy of solution of the AgCl solid to be positive 86 kilojoule per mole. Okay, so this is how you construct a thermochemical cycle and also figure out the enthalpy of the solution of AgCl. Now we're going to focus on the next part, which is B. So we need to arrange the following substance in ascending order of the lattice energy. So ascending order adalah dalam keadaan meningkat dari rendah lattice energy yang rendah from the low to high lattice energy. Okay, so between these three we need to arrange that. So from here we can say that this ionic solid consists of cation as well as the anion. So we're going to have Na plus Cl minus. For here, we're going to have Mg2 plus and Cl minus. And from here, we're going to have Al3 plus and Cl minus. So you know that the factor here is the cation, Al3 plus, Mg2 plus, and Na plus. Okay, so from here, the higher the ionic charges, lagi tinggi charge tersebut, maka makin kuatlah ikatan dan lagi banyak energi diperlukan untuk memecahkan the lattice or the ionic solid. So in order to put that into words, let us start with drawing or making the sequence first. So as what I said that, NaCl going to be the lowest, followed by MgCl2, and then followed by AlCl3. So we're going to make a comma, and then we're going to make an arrow, and we're going to put as the ascending order of the lattice energy. Or alternatively, you can also written that as NaCl is lower than the MgCl2, and then AlCl3 is greater than MgCl2 and greater than NaCl. So both of this way is being accepted. So the reason is, first, this is because of the ionic charge increases from the Na plus, Mg2 plus, and Al3 plus. So when the ionic charge increases, the stronger force of attraction is experienced in AlCl3 towards the Cl minus ion. And as a result, more energy is needed to dissociate respective ion from its ionic solid, and hence the lattice energy of AlCl3 is the highest, followed by MgCl2 and NaCl. So this is how you make the sequence and provide the explanation step by step. Okay, so we're going to move on to the next question. So now for question 3, an electrochemical cell is constructed from the following two half-cell reaction. So VO2 plus aqueous reacting with 2 mole of H plus aqueous with electron in order to produce VO2 plus aqueous as well as water. And it's going to have the SRP value of E naught equal to 1.00 volt. And the other equation is the Pb2 plus aqueous accept 2 electron in order to produce Pb solid. So for 3a, we need to write a balance equation for the overall reaction when the two half cells are connected. And in order to answer this question, we need to write the equation at anode and cathode first. So for the reaction at anode or cathode, we need to look at the SRP value given, standard reduction potential. So both of these equations are in reduction state because it accepts electron. Dua-dua menerima elektron. Okay, so from the SRP value here, the more positive value, which is this one, will be at the cathode. Meanwhile, the more negative value will be at the anode. Okay, so this is the easiest way to determine that. So for the equation at anode, it's going to be the reaction of between the Pb solid, and then you know that anode will be the place where oxidation happens. Okay, so when oxidation happens, we need to reverse the equation. So we know that Pb solid is going to produce Pb2 plus aqueous ion plus 2 electrons. Okay, because it is being flipped. This one is reduction, but this one is oxidation. Meanwhile, for cathode, we just write back this equation, but we need to multiply that by 2. Okay, the reason we multiply by 2 because it have 2 electrons here. So the whole equation here is multiplied by 2 so that we can cancel out the 2 electrons. So the cathode, we're going to write back, which is 2VO2 plus aqueous ion. 2 times 2H plus is going to be 4H plus. The electron become 2 electron. And then VO2 plus here going to be 2VO2 plus. And then 2 mole of water. Okay, so the next step is we're going to cut the electron, 2 electron. And then cut another 2 electron at the back. So the balance here, we're going to write it back here. So we're going to have the Pb solid. So for the overall Pb solid, this one, plus with 2VO2 plus aqueous ion, and then plus 4H plus aqueous ion. Okay, so this is on the reactant side. And then you're going to have the arrow. So we're going to put the product. So in the box, which is Pb2 plus aqueous, 2VO2 plus aqueous, and then 2 mole of water. So everything has been written down. Okay, so ensure that you have the phases all written. Okay, now we need to calculate the standard electrode potential for the reaction. So in order to calculate the standard electrode potential, we need to use the formula of E naught cell equal to E naught cathode minus E naught anode. So in order to use this equation, we need to use the SRP value, standard reduction potential value. So here are the values. So you just directly take it from the given here. So at cathode, the reaction here gonna be 1.00 volt. Okay. Meanwhile, at anode, because we already put the negative, you just plug in the SRP value at anode. So at anode is equal to negative 0.13. Okay, so you're gonna put bracket negative 0.13. So negative with negative gonna become positive. So it's gonna be positive 1.13 volt. Okay, so this is how you find the standard electrode potential. Now for question number C, we need to calculate the initial potential at 25 degrees Celsius if the initial concentration of the VO2 plus is 0.1 molar, H plus is 0.05 molar, VO2 plus is equal to 0.1 molar, and the Pb2 plus is equal to 0.25 molar. So in order to find the initial potential, we need to use the formula of E cell. Okay, so our formula of E cell is equal to the E naught cell minus 0.05 and 0.0592 divided by n log q. And our n here is equal to 2 because n here refers to the number of electrons. So the number of electron transfer is 2. Okay, so we're gonna do the substitution. So E naught cell is calculated from the B part here, which is 1.13, 0.0592 written back, n is equal to 2, number of electron, and then log our Q here is basically our reaction quotient. So our product is Pb2 plus, and then the other product here is VO2 plus aqueous. So VO2 plus aqueous, and then number 2 here will be power up. For the water is not included because it is in the liquid state. So kita abaikan yang liquid state. Bahagi or divided by the concentration of the reactant. So solid we're going to ignore, same to liquid. So we're going to take the aqueous because of the concentration here. So we have VO2 plus, stoichiometry here is 2, so it's going to be to power of 2, and then H plus to the power of 4. Okay, so it's going to become like this. Okay, double check. And then once we settle that, we're going to plug in the value that is given in the equation. So similarly, we're going to put it back. Log Pb2 plus is 0.25. Okay, correct. And then our VO2 plus is 0.1. Okay, correct. And then our VO2 plus, VO2 plus. So our VO2 plus is going to be 0.1, correct. And then our H plus is 0.05. Okay, so don't forget the power, to the power of 2 to the power of 4 here. So you can calculate inside your calculator on this part first. Okay, so inside the calculator, when you settle this term here, you're going to equal to 1.13 minus 0.1362. Okay, so please put this value inside your calculator and then make sure that you get this value here. So 1.13 minus this value, you're going to get the value of the initial cell potential to be 0.994 volt. Okay, so therefore the initial cell potential is equal to 0.994 volt. So the unit is compulsory, similar to here. Okay, so that's all for question number 3. Now we're going to look into question number 4. So for question number 4, a hydrocarbon, which is the C6H12, exists in the two isomeric form A and B. Compound A decolorized from in water, whereas B does not. Compound A undergo ozonolysis to give a single product C. Compound C forms a brick-red precipitate when treated with copper 2 sulfate and sodium potassium tartarate in alkaline solution. So you have to deduce the structural formula of A and draw the structural formula of B. So when you see the question deduce, you need to draw and give explanation. Okay, you have to give two things, the drawing of the structure as well as explanation in order to get the full mark. Meanwhile, for draw, you can just simply draw without the explanation. Okay, so the keyword of deduce here is important. Okay, so from here, you are given in the sentences dalam bentuk ayat ataupun perkataan. Okay, so it's really difficult for you to visualize. So what I'm going to suggest you to do is that you're going to create an idea scheme. So when you read the sentence by sentence, you try to make a scheme. So let's say I'm going to make my scheme to be like this. So my idea is that I have the C6H12, okay, which is a hydrocarbon. So the C6H12 can exist in two isomeric form, A and B. Okay, so boleh dapat daripada soalan. So A will decolorize from in water. Meanwhile, B does not decolorize from in water. And compound A will undergo ozonolysis to give single product C. Okay, and compound C here will form a brick red precipitate when treated with copper sulfate and sodium potassium tartrate in alkaline solution. Okay, so from the sentences form, I have changed that into the diagram form in order for me to see it more clearly. So I need to deduce the structural formula of A. Okay, so I know that the structure of A need to be an alkene. Kenapa alkene? Because it decolorized from in water. Meanwhile, for B, it needs to be an alkane. Okay, A, sini E. Okay, because it does not colorize from in water. Okay, and this alkene here, dia mesti symmetry or symmetrical. Why? Because it's gonna give a single product. Hanya satu jawapan sahaja yang sama bila dia undergo ozonolysis. So let's say you have C6H12. So you're gonna have 1, 2, 3, 4, 5, 6 carbon. Okay, so you know that the carbon-carbon double bond gonna be at the center. Okay, because when it undergo ozonolysis, so ozonolysis will have the reagent of O3 with zinc H2O. Okay, so when it undergo ozonolysis, it's gonna break this bond via oxidative cleavage. So what you're gonna get is aldehyde. Sebelah kiri akan dapat aldehyde. The same goes on the right hand side. 1, 2. Okay, so this structure and this structure is the same. So it's gonna become propanal. 1, 2, 3 carbon. 1, 2, 3 carbon. So both of that gonna be propanal. So it is a single product. Okay, so your answer cannot be like this, because when your carbon-carbon double bond, if it gonna be like this, you're gonna get two different product. Okay, you're gonna get one is ethanol. The other one gonna be butanol. Okay, so different product. So this answer will not be accepted. Okay, so that is why only this answer going to be accepted, because it says a single product of C. And then what is meant by this statement here, from a brick red precipitate bila react dengan copper sulfate and sodium potassium tartrate in an alkaline solution, is that the product here is an aldehyde, because it gives positive result to the Fehling test. Okay, so we know that our answer here is correct. Okay, so we're going to draw the structure of A properly. So I know that it is an alkene, has double bond because it decolors from water. Single product of C means that A is a symmetrical alkene. Symmetrical maksudnya kiri dan kanan adalah sama. Okay, and then this is my structure here, and the C will give positive result to Fehling test, which is the formation of brick red precipitate, because we know that C is an aldehyde as what I have shown in the equation here. So this is how you should answer question 4A. Alright. Meanwhile, for question 4B. Okay, so for question 4B, you know that it is an alkane. Okay, so alkane. If you were to draw your answer like this, 1, 2, 3, 4, 5, and 6, will your answer be correct? Correct or wrong? Okay, so in order to determine that, you need to count the number of carbon and hydrogen. So 1, 2, 3, 4, 5, 6. So ini adalah CH3, CH3, here is CH2, 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 CH2. So if you were to count the number of carbon, you're going to get 6 carbon. The hydrogen here going to be 3, 2, going to be 5, 7, 9, 11, and 14. H14. So you know that your answer here going to be wrong. So it cannot be a aliphatic alkane because it need to be C6H12. So it cannot be a single one to be like this. It cannot be aliphatic. What it's supposed to be is cycloalkane. Dia sepatutnya adalah cycloalkane. So contoh cycloalkane yang kita boleh bagi, is we can try to make a 6-membered cycloalkane, 6-membered ring. Let's say 1, 2, 3, 4, 5, and 6. Okay, so 1, 2, 3, 4, 5, 6. So when you count the number of carbon, you're going to get 6 carbon, and then your hydrogen, H and H, multiply by 6. So we're going to be C6H12. So this one is correct. You can also make to be 5 carbon, 5-membered ring. So let's say like this, and then you're going to make a branch here. So 1, 2, 3, 4, 5, and then you're going to make a CH3. Okay, CH2, 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 CH2. So you're going to get 8, 12. Okay, so it's still consistent, which is C6H12. Okay, or you can also make a 4-membered ring or 3-membered ring. So the answer here can be a lot of possibility. Boleh ada banyak jawapan lah. So you can draw any of those. So I'm gonna write down the answer properly, which is in digital form. So your answer can be a 6-membered ring. Let's say a cyclohexane, or you can draw cyclopentane with a branch, or cyclobutane with 2 branch, or a cyclopropane with 3 branch, which is 3 metal. Okay, so any of these answers will be accepted. So if you draw this one, you will also get the marks. Or if you draw the one, you also will get the marks. Alright. So now for question number 5, benzene can be converted to its derivative as shown in the reaction scheme below. So we have benzene converted by a process of D to produce the alkyl benzene, and then it's going to be a reaction here as well as a reaction here. So from the equation number 5, we need to name the type of the reaction D. Okay, so from benzene, it's going to become alkyl benzene or ethyl benzene here. Okay, so for this reaction, it is known as the name gonna be Friedel Kraft alkylation. Okay, Friedel Kraft's alkylation. However, they ask you about the type. Okay, so the type of the reaction here is the electrophilic aromatic substitution. So one of the hydrogen, doesn't matter which side, is being substituted with the alkyl group. So it is an electrophilic aromatic substitution reaction. And then for B, ethyl benzene, okay, can be converted into styrene. So this one is styrene, and here is ethyl benzene. So ethyl benzene can be converted into styrene by a 2-step reaction, which is E and F, such as E and F. Okay, so what's going to happen here is that from the alkyl benzene, what we can do is we can form a haloalkane at the side chain dekat bahagian tepi ini. Okay, so kat sini, what we're going to do is we're going to change one of the hydrogen into halogen, let's say Br, and then it's going to become CH3 here. Okay, so alkane is going to become haloalkane at the side. So the reagent for E going to be bromine with UV. So you can say that E is equal to bromine molecule with UV. So it will undergo free radical substitution where hydrogen is being converted with the bromine, and it's gonna take over the middle side because it is a much more stable radical. So it's gonna produce a secondary haloalkane. So Br gonna place here instead of this side. Okay, and from here, from the Br, it's gonna produce an alkene. So we're gonna remove the Br again, and then we're gonna remove one hydrogen from the neighbor, which is on this side. So what we're gonna do here is that, as what you can see, if we were to expand, we're going to remove H and Br. So it will undergo the process of D maksudnya buang ataupun elimination. So hydro means we remove hydrogen. Halogenation means that we're going to remove halogen group, both hydrogen and halogen group. So we will undergo the process of dehydrohalogenation, which is the elimination. So for the reaction, in order to remove halogen and hydrogen, we're going to have the reagent of KOH, ethanol with reflux. Okay, so these are the two reagents that you needed. So when you remove HBr, an alkene going to be produced, which is the styrene. Now we need to draw the structural formula of compound H. Okay, and since I mentioned before, when we use bromine with UV, we're going to produce a major product where it's going to replace the hydrogen at the center instead of the side. Okay, so hydrogen yang di tengah-tengah yang akan substituted, bukannya di tepi. So H going to be the structure to be like this. Okay, so now we're going to continue with question number 5D, where we have to write the mechanism for the reaction involving G. So from here you have your ethyl benzene, but now the bromine molecule will be attached at the para position at carbon number 4. 1, 2, 3, and 4. So from here we know that it will undergo the process of halogenation, where it's going to produce where you're going to need Br2, but now it involves FeBr3, which is an acidic catalyst. Okay, so Br will be used in order to replace the H at the benzene. Okay, so Br2UV here will affect the alkyl group, but Br2FeBr3 will affect the hydrogen in the benzene group. Okay, so that's the difference. Okay, so we're gonna need these two reagents in order to proceed with the production of this product, and we're gonna show that in the mechanism. So as usual for the mechanism of benzene, it's gonna involve three important steps. So step number 1 is the formation of electrophile. Step number 2 is the formation of the uranium ion. And step number 3 is the deprotonation of the uranium ion. So we need to produce our electrophile first. So our electrophile will be consisting of our reagent. So we have bromine molecule, and then we're going to have our FeBr3, which is our catalyst. So the bromine molecule will have the lone pair. So the lone pair is used in order to attack the catalyst in order to produce a complex. Okay, so this complex here, the FeBr3 will carry a partially negative charge and a partially positive charge here. So we're going to put the electrophile here again in step number 2. Okay, so when we have our electrophile, now we're going to write back our nucleophile, okay, which is our starting material here. So our starting material will react with the electrophile that has been produced in step number 1. So the nucleophile, which is electron rich, will attack the Br, and this is going to break the bond in between these two bromine atoms. So what's going to be produced here is the uranium ion. So you're going to have the benzene ring attack one bromine. So you're going to be bromine attaching here. And this carbon-carbon double bond will become carbon-carbon single bond. And it's going to carry a partially positive charge. And this positive charge here is can be at this side or can be that side, because the electron can be delocalized. So let's say if the electron moves here, the positive charge will be at this position, at this corner here. And at the same time, this electron can also be moved inside here. So it's gonna make the positive charge to be at it's gonna be at this end here. Okay, at this corner. Okay, so as what you can see here is that the electron will be delocalized. So for all of these things, it shows that it's going to have a formation of the uranium ion. Okay, so uranium ion has been produced. But in step number 3, we're going to deprotonate that. So deprotonate means we're going to remove the hydrogen. So we can choose any of our uranium ion. Let's say I'm using this uranium ion at this last part here. So I'm going to copy back into here and I'm going to remove the hydrogen. Which hydrogen? So I can choose this hydrogen here. Okay, let's say I'm going to break the bond here from the complex of this one. So the Br, which have a lone pair, will attack the hydrogen, and then this hydrogen will be removed, and it's going to form the double bond back. So as a result, I'm going to produce the Br with CH2 and CH3 here. Okay, so here is our starting material. And at the same time, I'm going to produce HBr as well as the FeBr3. So my catalyst is gotten back, okay, because catalyst is not involved in the reaction. It only increases the speed of the reaction and helpful for the reaction to occur effectively. Okay, so here are the mechanism that is shown for question number 5. Now for question number 6, we're gonna do the dehydration of the 2-methyl 2-butanol that can produce alkene. So for question number A1, we need to draw the structural formula of all the alkenes formed, and we need to label the major product and explain the answer. So the 2-methyl 2-butanol will have a formula of 1, 2, 3, and 4 carbon. Okay, so the 2-butanol will have OH here, carbon number 1, carbon number 2, carbon number 3, carbon number 4. And then at carbon number 2, it's going to have methyl group. So it's going to become CH3 here. Okay, so you can have the structure to be like this lah. OH upwards or OH downwards is the same. Okay, so just erase this one. 1, 2, 3, 4. So it's going to be 2-methyl 2-butanol. And as what you can see here, we will undergo the process of dehydration. Kita akan buang air, which is our H2O. It means that we're going to remove OH with hydrogen. So OH we're going to remove, and we can remove the hydrogen from the adjacent carbon. Okay, ini adalah carbon ini. Kita kena buang hydrogen daripada carbon di jiran dia. So let's say if you're going to remove OH and hydrogen here, we're going to get a double bond here. So that's our first possibility. Okay, for our second possibility, we can remove OH and then the hydrogen from the adjacent carbon daripada jiran dia, OH and H here. So if we were to remove on this side, we're going to get the carbon bond at the carbon-carbon double bond at the middle here. Okay, so we're going to have A structure or the B structure. Okay, so from A and B possibilities, we need to label the major product. So from here, I know that my major product going to be B. Why is that? This is because the B is the most substituted alkene, as the carbon-carbon double bond of the carbon-carbon double bond is attached to more alkyl group in comparison to A. Okay, so this carbon here is attached to 1 alkyl group, 2 alkyl group, and 3 alkyl group. Meanwhile, for here, this carbon will attach with 1 and 2. Okay. Manakala di sini, carbon ini dia tidak melekat kepada apa-apa alkyl group. So in overall, it's going to have 2 attachment. But here, 1, 2, and 3. Okay, so by right, this one will be attaching with more alkyl group and it is a more substituted alkene. And this is consistent to the rule that you have learned, which is the Setzaff rule. Okay, so you need to mention these 2 explanations here. Right? And now for question 6b, 2-bromo 2-methyl butene can be converted into 2-methyl 2-butanol. We need to write the mechanism for this reaction. So as usual, you need to write this compound first in order to get the idea. So butane 1, 2, 3, and 4. And at carbon number 2, you're going to have the CH3, and then you're going to have Br here. So as what you can see here, that one you need to convert into this one. So Br need to be converted into OH. Okay, So Br need to be converted into OH. So you know that you need to suggest the reactant that can be used in order to replace Br with OH. So for me, I'm going to use the KOH aqueous reflux. So KOH aqueous reflux means that it's going to have the KOH as well as AQ means water, H2O. And from here, my OH will going to replace the Br. So I'm going to use the nucleophilic substitution. And since this is a tertiary haloalkane, okay, so carbon ni adalah tertiary carbon and then dia adalah tertiary haloalkane. So it will involve two steps and it is an SN1 mechanism. So when it is an SN1 mechanism, we're going to use the weak nucleophile. So weak nucleophile here is water, which is our H2O. Okay, so our nucleophile going to be water instead of KOH. Okay, so kita tak boleh menggunakan OH minus, tetapi bila SN1 kita mesti menggunakan weak nucleophile, which is our water. Okay, so it will be acting as a nucleophile. So for SN1, it will involve two steps. So the two steps are where the step number 1 is the formation of carboxylic ion, and step number 2 is the nucleophilic attack on the carboxylic ion. So for step number 1, we're going to draw back our 2-bromo 2-methyl butane, and then it's going to break the bond by itself from the CBr. Okay, and then this going to produce a carboxylic ion here. Okay, so this is why the name is formation of the carboxylic ion. So it is a slow reaction. Meanwhile, for the nucleophilic attack, when the carboxylic ion is being formed, we're going to use our water as the nucleophile. So we're going to draw our water molecule, and then this water molecule will have the lone pair. So the lone pair will be used in order to attack the positive charge of the carboxylic ion. So when the water is attacked, the oxygen will be attached to this carbon here to become like this. Okay, and then another molecule of water will be used in order to take up the hydrogen, and this bond will be break apart, and then this going to be forming a OH here because O double bond, O lone pair, and then you're going to have H, and then another one here. This one is originally there, so dua, and then dua lagi ditransfer jadi dua. Okay, so it's going to become like this. So here refers to OH. Okay, so this is how you write the mechanism for the SN1 reaction for the conversion of 2-bromo 2-methyl butane to the 2-methyl to butanol. Now we're going to move on to the question number 7. So compound K and L are isomers of a branch alcohol. Alcohol yang berangkai with the molecular formula of C4H10O. Oxidation of K produces a carboxylic acid, whereas the L resists oxidation. So resist means here it will not undergo oxidation. Okay, and for question number 7 here, we need to deduce the structural formula of K and L. As mentioned, for deduce, you need to draw and you need to provide explanation. Okay, and for question number B, we need to write a chemical equation for the oxidation of K. Okay, so they give the idea here using sentences. And for me, I will always start off with a reaction scheme, which is using the idea. So I'm going to write again, where I know that my compound, which is C4H10O, is the isomers of the branch alcohol of K and L. Okay, I know that it is a isomers. So K and L here is a branch alcohol. Okay, so oxidation of K will produce a carboxylic acid. Meanwhile, L will not undergo oxidation. So dia adalah resist to oxidation. So we will see there's be no observable changes. So now we need to deduce the structural formula of K. So K oxidized to carboxylic acid. So we know that in order to produce a carboxylic acid, K needs to be a primary alcohol, because only primary alcohol can be oxidized into carboxylic acid. And the other information that we know is that K is a branch alcohol and not linear. Okay, so we can try to estimate, let's say, because we know that the formula here is C4H10O. So we know that we're going to have 1, 2, 3, 4 carbon, and then OH here. Okay, so here is a primary alcohol, and the primary alcohol can be oxidized into carboxylic acid. So 1, 2, 3, 4, and then this is going to be the double bond O, and then OH here. Okay. However, this is a straight chain, not a branch alcohol. So we know that this idea is wrong. What we're going to do is we need to make the branch alcohol. So how can you make it branch? Is you can change, let's say 1, 2, 3 OH here, and then one of this carbon here can be used in order to make branch either on this side. Okay, so I can make the carbon on this side. Okay, so what I'm going to get is the structure to be like this. Okay, I cannot put the carbon on here because when it become like this, it's going to be wrong, because when it is oxidized, the secondary alcohol will produce a ketone. Okay, so it does not satisfy the idea. Okay, and that is why we can only come up with one answer, which is the branch need to be on this carbon here. Okay, and for L is the branch alcohol and it resists oxidation. So when it resists oxidation, we know that it is a tertiary alcohol. Okay, so when it is tertiary alcohol, we have CH 1, 2, 3, CH3, CH3, and then CH3. So when you try to count the number of carbon, you're going to get C4, H10, O. So it is consistent to what you have here. Okay, so similarly, you can also count the number of carbon in K. So you have 1, 2, 3, 4 carbon. You have CH3, CH3, H, H, and H. So you're going to be C4, H, 6, 7, 8, 9, 10, and also O. So you know that this idea here is correct because the molecular formula is correct. Similarly to here. Okay, and don't forget to put your explanation downwards. So L is a tertiary alcohol and it is resistant towards oxidation. So this is how you answer the deduction question. And now for the next part, we need to write a chemical equation for the oxidation of K. So chemical equation. So we need to write our reactant again plus our reagent for oxidation. So oxidizing agent here is the strong oxidizing agent. For example, is the KMnO4 at acidified condition with heat. Okay, mesti ada ketiga-tiga condition for it to proceed. So we're going to put our reagent plus our oxidizing agent KMnO4 H plus with heat, and this will convert our primary alcohol to become a carboxylic acid. So you're going to have a branch here because it was stated in the equation it needs to be a branch alcohol. So this is how we do question number 7. For question number 8, the structural formula of the propionephenone is shown below. So compound M and N are isomers of the propionephenone, where M reacts with the solution of iodine in aqueous sodium hydroxide solution to form a yellow precipitate. So here is the iodoform test. Meanwhile, N, which is the isomers of this propionephenone, will rotate plane polarized light and forms a silver mirror when treated with Tollens reagent. So it gives a positive result towards a Tollens test. So in order to understand this statement better, as usual, familiarize yourself with making an idea. So idea is the reaction scheme. So when you make the idea, you will know that you have the propionol. So compound M and compound N, they are the isomers of the propionol. And for compound M, it's gonna react with the iodine solution in NaOH aqueous solution in order to form the yellow precipitate. Meanwhile, for N, it's gonna rotate the plane polarized light and forms a silver mirror when treated with the tolerance reagent. So here are the information that you have get. And from here, you can make some explanation or some deduction. So based on question number 8, they ask us to deduce the structural formula of M as well as N. As mentioned, when the question asks for deduce, you need to give the drawing with explanation. Okay, so there are two things that you need to do. So from the information that has been given, you can deduce something. So for M, when it gives a positive result towards the iodoform test, you know that the structure M here will have a methyl carbonyl group, where the methyl carbonyl group will be looking something like this, where C double bond O, CH3. So the structure of M need to have this structure. Meanwhile, for compound M, it rotate plane polarized light. So when it rotate plane polarized light, it means that it is an enantiomer where the enantiomer will have a chiral carbon. So chiral carbon means that it's going to attach with four different groups or four different atoms. Okay, and the other statement here, which is form silver mirror when treated with tolerance reagent, it means that the structure of N is an aldehyde because it gives a positive result towards the tolerance test. Okay, so you know that it is an aldehyde. So for now, let us deduce the structure of M first. So M will need to have this structure, and this is the isomers. So for M, you can imagine it to be like a benzene ring, and then it's gonna have this structure, C double bond O, CH3, and then it's gonna have the CH3 here. Okay, so this can be one of the possibilities of their isomers. So for M, at first you can get this kind of structure. So the number of carbon, hydrogen, and oxygen is still maintained because it is the isomer. Okay. Alternatively, you can also change the branching from this side in order to make it on the other side here, which is CH3. Okay, so this another possibilities, another answer. Or you can also change the CH3 here to be at this para position. Okay, so here is the another answer. So all of these three answers are accepted. Okay, and also let's say you don't want to make a branching, but you want to make it like this. For example, 1 and 2, and then C double bond O CH3, and then you're gonna have CH2 here. This is also accepted, okay, because it still have a methyl carbonyl group, and the molecular formula is still maintained. So that structure will also be accepted. So there are four possible answers for M. Okay. Now we also need to give a explanation. So the explanation here is the same as the deduction that we have made earlier. So it gives positive result towards the iodoform test, and therefore it needs to have a methyl carbonyl group. Okay, so whatever the structure that you drawn, as long as either one of those, it's going to be a correct answer. Now we're going to draw the structure of N. So we know that N is an aldehyde. So you can draw the structure of aldehyde with having a chiral carbon here. Okay, so this chiral carbon will attach with 1, 2, 3, and 4 different groups of atom, and therefore it is a chiral carbon, and it also have a aldehyde group. So you can make an explanation saying that it contains a chiral carbon which attached with 4 different groups, and then it's going to have a positive result towards the tolerance test where it's going to have the aldehyde group. Okay, so you might be wondering, sir, can I draw the structure to be something like this? Okay, so you want to draw the aldehyde here, and then you want to draw the CH3 here. So if you were to draw that one, this answer is wrong because it does not have chiral carbon. Okay, tiada chiral carbon dalam molekul tersebut. Jadi jawapan ini adalah salah. Okay, so let's say if you were to draw something like this, CH2 and double bond OH like this. Okay, so this one will also be the wrong answer because it still does not contain any chiral carbon. So there's only one answer is accepted in the molecular formula for N, the drawing of N. Okay, so it needs to fulfill both situations, chiral carbon and then have the aldehyde. Okay, and for question number B, we need to draw the chemical equation for all the reaction involved. So for M, you can select any structure from the 4 possible answers just now. So let's say I'm drawing the structure of M to be like this. And then I'm going to react that with the iodine. Okay, because it says iodine solution. And it's going to contain NaOH aqueous. And the reaction of M with the iodoform under the iodoform test will produce a carboxylic ion. So this is my carboxylic ion, and then the Na plus will be close by to the O minus here. Okay, and as a result, a precipitate going to be formed, which is a yellow precipitate, which is CHI3, which is the triiodomethane or the iodoform. Okay, so this one is for M. Meanwhile, for N, you're gonna draw back the structure, and then you're gonna make the chemical equation. So your reagent is your tolens. So this is the tolens reagent, AgNH3 bracket 2, everything bracket to the power of with a positive charge, and then it is under the tolens reagent, right? So it's gonna have a basic condition, which is the NaOH. Okay, so similarly, you're going to produce a carboxylate ion with CH3 here, and then O minus, and then the Na plus. Okay, and you're going to form a silver mirror, which you're going to produce the Ag precipitate down. Okay, so this is how you deduce the structure of M and N, and then also making the chemical equation step by step. Okay. So for question 9, compound P and Q have a molecular formula of C3H6O2. Compound P has a vinegar smell, while Q has a sweet smelling odor. Compound P will react with phosphorus 5-chloride and releases white fume. Meanwhile, the acidic hydrolysis of compound Q will give two products. One of the products has the reducing properties. So for question 9a, we need to deduce the structural formulae of the P and Q. And as mentioned, deduce here means you need to draw the structure as well as provide the explanation. Okay, so from the sentences here, let us convert that into the idea scheme first. So we have the molecular formula of C3H6O2, and then this C3H6O2 is the isomers of P and Q. So P has a vinegar smell, while Q has a sweet smelling odor. So P will react with the PCl5 in order to release a white fumes. Meanwhile, the compound Q will undergo acidic hydrolysis, which is H2OH plus, in order to give two products, and one of the product will have the reducing properties. So from here, you know that your compound P, which having a vinegar smell, is basically a carboxylic acid. Meanwhile, the sweet smelling odor is the properties of an ester. Okay, so you have 3 carbon. So the most logical structure for the carboxylic acid P is 1, 2, 3 carbon. And then you're going to have double bond O, OH. Okay, so 1, 2, CH2 here, and then CH3 here. So you're going to have C, 1, 2, 3, hydrogen, going to have 6, and then oxygen going to have 2. So it is similar to the isomers here. Meanwhile, for the Q, it is an ester. So it's gonna have one of the product will have the reducing property. So from here, we know that it is an ester. So what we can do is we can make 1 and 2, and then it's gonna have O, okay, O here, 1 and 2 carbon, and then the other one is double bond, O, and then H. So it's gonna have the ester bond, and it's gonna have CH2, and then CH3 here. So the number of carbon is 1, 2, 3. Hydrogen gonna have 6, and oxygen gonna have 2. Okay, so ester is produced from the alcohol part and then the carboxylic part. Okay, so this is how we deduce P and Q. So let us draw it nicely. So P gonna have a carboxylic acid part, which is consists of 3 carbon, double bond O, OH representing a carboxylic acid, since it has a vinegar smell. Meanwhile, for Q, as mentioned, it is an ester. So it has the ester bond, okay? It has 3 carbon, and then it's going to have a reducing properties, because when it breaks down, it's going to have the alcohol group as well as the carboxylic acid group, okay? And once we deduce this structure, we need to write the chemical equation. So let us do that. So once we do the chemical equation, we need to write the structure P again, which is the carboxylic acid, and then we're gonna react that with the phosphorus chloride, PCl5. So from here, the Cl will take over the place of OH, so it's gonna become acid chloride, and then it's gonna produce a byproduct of POCl3 as well as the HCl. So this byproduct here need to be written. Okay, and HCl here representing a white fumes that has been produced. Okay, meanwhile, for the Q, which is the ester that we has suggested just now, when it is undergo acidic hydrolysis, which is H2O and H plus, because esterification is a reversible error. So from the alcohol and carboxylic acid, it can be forming an ester, and from ester it can be broken down back into alcohol as well as the carboxylic acid. Okay, so from here, ester can be broken down into alcohol as well as the carboxylic acid. So our alcohol part is coming from this side. So O here will become OH. Meanwhile, for our this part here, it's gonna have OH here. So you're gonna produce a carboxylic acid, because from alcohol and carboxylic acid, you're gonna remove OH and AH, so you're gonna get back that structure. Okay, so you're gonna get this alcohol and then this carboxylic acid. Okay, and as what you have realized, this carboxylic acid will have the reducing properties. Ada properties yang sifat penurunan dia. Okay, reducing properties. This is because it only contain 1 carbon. So this 1 carbon here is known as the metanoic acid. So metanoic acid is a special acid because it has a carboxyl group. At the same time, it has the aldehyde group. So it can be reduced. So it has a reducing properties. Okay, so we know that our structures is correctly drawn for P and Q. Okay, and for the equation, remember, you need to give the reagent and also the condition in order to give the product. Now we're going to focus on C. So for C, we need to show how P, okay, bagaimana P can be prepared from the bromoethane via a two-step synthesis. So as usual, you need to start with the drawing of bromoethane. So ethane will have 1 and 2 carbon, and then it's going to have Br here. Okay, so from Br here, you need to produce like this. Okay, so from 2 carbon, 1 and 2, you're going to produce 3 carbon. So the increase in the carbon chain will have 2 ways. So first, using Grignard reagent, okay, And second way is by producing a nitrile compound. Okay, cara nak menambahkan carbon chain ada dua cara. Grignard reagent dan juga formation of the nitrile compound. So let us look into the formation of Grignard reagent first. So from our haloalkane, so when we want to increase our carbon chain, we need to get into the Grignard reagent. So we need to use our magnesium, and the condition for the solvent is triether. So you're going to produce the Grignard reagent of MgBr. And from here, the Grignard reagent can be converted into carboxylic acid by reacting it with the carbon dioxide as well as the water. So what you're going to do is this part here going to be replaced with C double bond O OH, and therefore you're going to get 1, 2, 3 carbon. 1, 2, 3 carbon. So from 2 carbon become 3 carbon at the end. Okay, so this is one of the ways. The other way, okay, ini cara yang pertama. Cara yang kedua, you can also use nitrile compound. So you're starting from the haloalkane, and then you're going to react with the KCN aqueous ethanol under reflux condition. So it will undergo nucleophilic substitution, where Br here will be replaced by Cn, okay, plus and Cn minus. Okay, so Cn will take over the place of Br. You're going to become like this, and then you're going to undergo the process of hydrolysis, where the Cn here will be converted into carboxylic acid. So both of these ways can be accepted, and both of these steps will involve two-step synthesis. Okay. Now we're going to move on to question number 10. So for question number 10, amines can be classified into primary, secondary, and tertiary amines. By using an amine with the molecular formula of C4H11N, we need to draw the structural formula for primary, secondary, and tertiary amine. Okay, so the molecular formula here is C4H11N, and then you need to give example of primary, secondary, as well as tertiary. Okay, so the most easiest one is to start with the primary amine first, in which it have 4 carbon. So for the primary, when you have 4 carbon, so it's going to become 1, 2, 3, and 4. 4 carbon, and then the last one here will be attached with NH2. Okay, so if you want to check back, you're going to have 1, 2, 3, 4 carbon, and then you're going to have CH3, CH2, CH2, and then you're going to have CH2 here. So you're going to have C4H11 and then N. So you know that your structure here is correct for the primary amine. So this can be one of the example. Or if you want to draw a branch with 3 carbon, it is also okay. So let's say you want to draw something like 1, 2, 3, and then NH2, and then you wanted to make a branch here. So this one is also accepted. So when you try to count the carbon, the hydrogen and nitrogen, this molecular formula is still consistent. Okay, so you can make a branch here, or you can also make the branch at up here. Okay, so you can also draw to be something like this. Okay, or you can also make a primary amine, let's say to be something like 1 and 2 and H2 here. So 1, 2, and then 3 and 4. So all of these 3, 1, 2, 3, 4 is a primary amine. So you can draw your primary amine to be something like this with 4 carbon, or 3 carbon with a branch, or the branch you change into this position, or you make a double branch here at this carbon here. Okay, now you're going to make a secondary amine. So for secondary amine, the nitrogen here need to be attached with 2 alkyl group. So maybe you can do 2 carbon on this one side and the other carbon on the other side with hydrogen here. So when you count the number of carbon, 1, 2, 3, 4, you're going to get C4. And then H, you're going to get 3, 2, 2, 3, 10, and then got 1 here, 11, and so you know this structure here is accepted. Or you can also make like N, 1, 2, 3, 1, 2, 3 di sini, and then CH3 di sebelah sana. Okay, and then you're gonna have H here. Okay, and here can be like C, CH2, CH2, CH3. Okay, so this structure will also be accepted. Okay, or you can also make something like this, which is the isopropyl, and then a methyl, and then H. So it will also be accepted. Okay, so when you count the number of carbon, hydrogen, and nitrogen, it is still consistent of C4H11N. So for secondary amine, you can make something like this, or you can make 3 carbon on the left hand side, or 1 carbon on the right hand side, or you can make N isopropyl here, which 3 carbon, and then the other carbon here on the other side. Okay, so both of these 3 answers will be accepted. So if you draw either one, you are correct. Okay, now we need to focus on the tertiary amine. So the tertiary amine, you're gonna have the nitrogen, but then it needs to attach with 3 alkyl group. 1, 2, and then 3. But since we have 4 carbon, so one of this carbon here will have 2 chain. I mean 2 carbon here for 1 single chain. Okay, and then the other one is hydrogen. So it doesn't matter lah. So 2 here or 2 here. Or for this time, I'm going to use the number 2 here. Okay, so I'm going to draw my structure like this. So if I were to count back, I'm going to get my CH2, my CH3 here, my CH3 here, and then my CH3 here. So I'm still going to get C4H11N. So I know that my tertiary amine here is correct. Okay, so this is how you draw your primary, secondary, and tertiary amines from the molecular formula given. And then now you need to make or answer question number B here. So for question number B, you need to arrange the above amines in the order of the increasing boiling point. And then we need to explain the answer. So the highest boiling point going to be the primary amine. So primary amine adalah lebih tinggi takat didihnya berbanding kepada secondary dan juga tertiary. So you can draw the structure as well, or you can make a general statement like this. So primary gonna be having a higher boiling point than the secondary, and it's gonna be greater than the tertiary. Why is that? This is because the primary amine will having a higher boiling point because of it can form a higher number of the hydrogen bond. So the nitrogen here will have H and then H. So it can form more hydrogen bonding in comparison to the secondary amine which have 1 and tertiary amine where it cannot form any hydrogen bonding. Okay, so the tertiary amine cannot form hydrogen bonding between the molecule and only contains van der Waals forces. Okay, and from here you can say that the hydrogen bonding is a stronger force or a stronger bond than the van der Waals forces, and hence more energy is needed to break the hydrogen bonding in the primary amine because it can form more in comparison to secondary, and the least amount of energy is needed to break the van der Waals forces in the tertiary amines. Okay, so this is how you do the arrangement and also make the explanation step by step. Now we're going to look into question 11. So the dipeptide R has a molecular formula of C5H10O4 and 2. When R, which is the dipeptide, is heated with the dilute sulfuric acid, 2 amino acid as C2H5O2N and T, which is C3H7O3N, were produced. So compound T is optically active while S is not. So we need to draw the structural formulae for S and T. Okay, and once again, I will suggest you to start off with the idea in order to see and visualize the question better. So you know that you have a dipeptide R with a molecular formula of C5H10O4 and 2. And when it is heated with a dilute H2SO4, two amino acids going to be produced, which is amino acid S with a molecular formula of C2H5O2N and the molecular and another amino acid which is T, which is C3H7O3N. So S and T here is amino acid or amino acids. Okay, so the compound T is optically active. Okay, meanwhile S is not optically active. So optically active means that it is an enantiomers and then it's gonna attach with four different group of atoms, four different groups of atoms. So it's gonna consist of a chiral carbon. Okay, so in order to determine S and T, we can try to make a deduction from the molecular formula that has been given, which is C2H5O2N. Okay, so C2H5O2N will have 1 and 2 carbon. And then you know that for an alpha carbon, so the alpha carbon will have C here, C alpha, it will contain COOH and then NH2. Okay, so the most logical one, you have used up 2 carbon, C2, and then your hydrogen you have used up 3, but then you have 5. So you know that you need to attach with hydrogen, attach with hydrogen. Okay, so you know that you're going to have C2, and then hydrogen you're going to have 1, 3, 4, 5, C5. Oxygen you're going to have O2, and then you're going to have N. So you know that this is your structure for S. Okay. Meanwhile, for T, you know that it's going to consist of 3 carbon. Okay. And for the alpha carbon, it's going to consist COOH and then the amino group. Okay. And from here, you have used up C3, and then nitrogen you have used up, oxygen you only use up 2, and then hydrogen you have used up 3. Okay, so H3 here. Okay, so you need to use up another hydrogen, and then you need to use up 4 oxygen. Okay, so the most logical one is to put CH3 here. Okay, so you're going to get, because you have used up 3, so you're going to left with OH. So you can make OH here. Okay, so as what you can see here, this carbon here is a chiral carbon because it is attached with 4 different group of atom, COOH, amino group, OH group, and the methyl group. So this is one of the possibility of T. Okay, so we have identify S and T from the molecular structures that have been given. And by knowing that alpha carbon will be attached with amino group and the carboxyl group. So for S, this is going to be my structure. So you can draw it in terms of the condensed or expanded structure, or you can also draw it in terms of the skeletal structure. Doesn't matter, as long as the number of carbon, hydrogen, oxygen, and nitrogen is consistent. Meanwhile, for T, this is going to be my structure here. Or I can also draw it to be something like this. Okay, so OH here can also be attached at the end, and this here is still a chiral carbon because it still contain the carbon here will still attach with 4, with 1, 2, 3, and 4 different groups. Okay, so it doesn't matter. Okay, and now I need to draw the structural formula for R and label the peptide linkage. Okay, so in order to see it better, let us draw it one more time. So for my S, I have my structure to be like this, right? Double bond O, OH, and H2. Okay, and then this one is my S. For T, my structure, I'm choosing this one. So my structure gonna be like this, OH, and then I'm gonna get OH downwards, and then here, and then I'm gonna put NH, and the NH2 I'm gonna expand, and H, and then H here. Okay, why should I expand? This is because I want to show that by removing of OH and H here, an amide bond gonna be formed. So I'm gonna eliminate water. So when I do that, I'm gonna get the structure of double bond O and H2, and then because OH and H gonna be removed, this will be attached with N directly, H, and then I'm gonna get the structure to be like this, 1 and 2, and then like this, then OH here. Okay, so this is gonna be my structure for R. Okay, and this is how if I were to draw it digitally. Okay, so from S and T, I'm going to eliminate because this is a condensation reaction. We're going to remove water, and then an amide bond going to be formed. So I'm going to cancel this again. I'm going to erase this, and we're going to focus on here. Okay, and from here you need to label the peptide linkage. So what I'm going to do is I'm going to show this area is where the bond is being formed, and then I'm going to make an arrow from this position showing that this is the peptide linkage in order to get the full mark. So make sure that you label and then make an arrow and put the peptide linkage there. Alright, so that's all for question 11. So for question number 12, polytetrafluoroethene (PTFE) is commonly known as Teflon, is used as a non-stick coating for pans and other cookware. Okay, so this is the structure of the polymer, and then we need to state the type of this polymer. Okay, so we know that the repeating unit, this polymer here will have CF, 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 and CF. So it is repeated few times. And this type of reaction will have a single bond. So you know that it is coming from a carbon-carbon double bond. And then you're going to have F here, F here, F here, and F here. Okay, so when you have a lot of monomers with the presence of peroxide, it's going to initiate a radical. So it's going to go on the right hand side and it's going to go on the left hand side. So it's going to produce like C, single bond C, F, 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 and then you're going to get the attachment on the left hand side and the right hand side with the N here showing a polymer. N at the front is monomer, and at the back is polymer. Okay, so we know that the monomers will have a carbon-carbon double bond. So a carbon-carbon double bond become a carbon-carbon single bond. It is an addition polymerization. Okay, and for the drawing of monomer, we're going to draw this structure once again. So you can draw to be expanded like this, or you can make it N. If you want to make it condensed, it's going to become CF2, CF2 like this. Okay, so drawing like this is also correct, or you can draw it to be like this. Okay. Okay, I think that's it, the discussion for the past equation 2020 and 2021. So I think that's all for today's video. See you again some other time. Bye.